Okay, let's get started. My name is Sharad Mishra. I work for Intel Corporation. And I've been contributing to OVSDB project for about 10 months now. And I have with me today Eric Multanen from Intel. And he's a contributor to OVSDB project. And I have Danny Zhou, also from Intel. And Danny focuses primarily on service function chaining project. And today, we'll be talking about enabling data plane development kit accelerated open vSwitch in ODL and accelerating SFC. So just a show of hands. How many of you know what is DPDK? That's pretty good. So for the rest of you, what I'm going to do is I'm just going to give a brief overview of what is DPDK, just to level set. And then we will talk about DPDK accelerated open vSwitch. And then we'll go over and talk about what work went into the Lithium release of OpenDaylight for enabling DPDK in OVSDB southbound. And we'll talk about more work that needs to happen in ODL for DPDK enablement. We can work on it in Beryllium release. So we'll talk about those plans that we have. And then we'll move over to service function chaining. And we'll talk about the performance improvement that we are seeing with DPDK in service function forwarder and service function classifier. And we'll also discuss the plans that we have around DPDK in SFC project. So this is not a DPDK presentation. As I said, I'll give a brief overview of DPDK and then level set everybody here about what DPDK is. I only have 2 slides on DPDK. And what I want to drive home with these 2 slides is the motivation behind enabling DPDK in ODL. So why DPDK, and what does DPDK bring to the table? So what is data plane development kit? DPDK is open source software that improves packet processing on Intel architecture. And how it gets this improvement is that it bypasses the Linux networking stack and maps the hardware registers onto the user space. And then it provides a bunch of libraries like buffer management, queue management, memory management. And it also gives you some sample applications when you download from dpdk.org. And those sample applications are like L2 forwarding, L3 forwarding. And if you are a developer interested in writing your own DPDK-enabled application, you can look at those sample applications to get an idea of how to write your own DPDK application. So apart from bypassing the slow networking stack, what DPDK also does is it uses pole mode driver, it uses batch packet processing, and it uses run to completion scheduling. So all those things combined together give DPDK a big performance boost. As you can see on the slide, this is running on Intel Open Networking Platform system L3 forwarding using DPDK and then without DPDK. And what you see here is the most gain in the performance you get on the smaller size packets. So for a 64-byte size packet, you go from 1 million frames per second to almost line rate. So that kind of improvements is what you see with DPDK. And that is the motivation for doing this enablement in ODL. And what we want is the consumers of ODL like OpenStack to use this information about the platform that they are managing, and then using that information, smartly provision the VMs. Now I'll invite Eric to come on the stage and talk about DPDK OVS.
All right, thanks, Sharad. My name is Eric Multanen, and I've been working with OpenDaylight and the OVSDB project for, well, at least a couple years, actually. But like Sharad said, we just started coding in the last 10 months or so, basically the lithium cycle. So like Sharad indicated, DPDK is basically a library. It can be used for applications and a number of different things. What I'll talk about here now is, and again, this is a kind of an overview. It's not an in-depth study of Open vSwitch with DPDK, but basically using DPDK to accelerate the data path of Open vSwitch. And so I'll give you guys a brief overview of that, and then talk a little bit about how that gets enabled in Lithium in the OVSDB southbound plugin, and then we'll move from there. So the diagram here is kind of showing at the bottom right there, it shows kind of a diagram view of Open vSwitch with DPDK, DPDK data path. One of the key things to, well, and then it shows it kind of in context with OpenDaylight and also OpenStack on top. From a control perspective, from OpenDaylight talking or communicating with the OVS with DPDK, there's not really any difference. It's OpenFlow and OVSDB. And generally, it's the same. And the point today is to talk about some of the differences that pop up. So first one is OVS with DPDK NetDev. Uses the NetDev data path, which means that the data path runs in user space. It's not the kernel-based data path user space, and you can kind of, if you can see that in the diagram, it shows that the forwarding plane is up above the kernel space. And so that introduces a few issues that ultimately we need to work out and resolve as we integrate with some of the other OpenDaylight projects. The other thing that gets introduced with OVS with DPDK is a number of different or new interface types. So the first one I'll call out is the DPDK. So I've listed the actual types. These are the strings that show up if you were to list the interface table in OVSDB. You would see these as the type of that interface. So DPDK is the physical port. So because the data path is running in user space, the physical port is also managed by DPDK in user space and uses what we call a pull mode driver. And Danny will probably talk a little bit more about that in his presentation. But you see it there in the diagram called PMD. And so that type of port shows up as DPDK type. DPDK-R, the next type there is a DPDK ring device. That would be an interface that would be used for an application to connect to the data the forwarding plane, like a VM or something. And this is kind of special. It's basically a shared memory kind of interface. And so the application or the VM that uses this type of interface also has to have special interface or special device to interact with that type of interface. So I'm showing it here, but it's not one that we've currently experimented with ourselves. Other folks have. And then the third one I'll call out is the DPDK vhost user interface. And this particular type of vhost user interface is introduced with the version of Open vSwitch that's built with the DPDK 2.0. So that's kind of one of the most recent builds of OVS. And what that gives you is the DPDK vhost user interface provides the performance benefits of DPDK, but also provides to the VM a kind of a standard vhost or VirtIO type of interface. So the VM doesn't really have to know that it's what kind of data path or OVS is running underneath. Finally, and this was something that we helped get pushed into the Open vSwitch code, is in the Open vSwitch table, which kind of represents, that Open vSwitch table represents the information about the OVS node where OVS is running. There's a couple new columns, data path types and interface types. And these basically are a list, an enumerated list of the data path types supported by the Open vSwitch instance, and also the list of interface types. So if you were to query that, you would see, like in the interface types, you'd see a list of maybe a dozen, all the dozen interface types supported by that vSwitch. And the purpose of this is that if you query that information, you'd see, if you saw DPDK and DPDK vhost user included in that list, and also the data path types includes the netdev type, then you could deduce that this particular instance of OVS is actually OVS with DPDK. All right. So those are some of the things that, from like OpenDaylight's perspective and from the schema, that would be sort of differences that OpenDaylight could detect when it's interacting with a particular, with an OVS with DPDK instance. So in the Lithium release of OpenDaylight, what we did is, well, first of all, and again, this is not an overview of the southbound plugin of OVSDB and Lithium, but one of the key things that happened with that plugin is it was converted, or essentially rewritten to use the MD sal. It used to be written based on the AD sal. So what that means is a topology model. The topology model is augmented to support the OVSDB schema. So basically, significant elements of the OVSDB schema were basically mapped to the Yang model, a Yang topology model. And I'll just call out the few things that are relevant to OVS DPDK here. So the topology node, there's an augmentation that maps to an OVSDB node or an OVSDB host. And that basically contains information about the actual OVS host itself. And included in that model is the interface types and data path types that I mentioned previously. So one can query that node and find out, does that node support DPDK type ports or not? Another topology node augmentation was created for the OVS bridges. So a given OVS node may support multiple bridges, and there'd be multiple nodes mapped to each one of those bridges. And part of that augmentation for the bridge node is the data path type, which would either be of type netdev or system, I think, is the default type. And netdev by itself doesn't mean it's a DPDK node, because it could be the normal or the old netdev style node. So you'd have to look at that first information in the OVS node to find out if it's a DPDK style bridge. And finally, the OVSDB ports and interfaces were modeled in the Yang using the termination point object that's part of the topology nodes. And included in, so that augmentation includes all the, relevant information about the OVSDB ports and interfaces. Relative or important for DPDK support is the interface type. So that's basically the elements of the OVSDB southbound plugin and the Yang model that have been introduced in Lithium that are important for the supporting DPDK-based OVS. And finally, so where we are now then is, as we look into the beryllium time frame, is what we'd like to do is make sure that OVS with DPDK is actually working well with things, things like NetVert, the OVSDB NetVert project, which interacts with OpenStack. And like I mentioned, the DPDK vhost user interfaces. So if you have a VM and you connect it to a DPDK-based OVS, you want to use the vhost user interface because that gives really good performance. If you don't, then you get the old style VirtIO, and then the performance is much less. So that requires a little bit of interaction with the OpenStack ML2 drivers for ODL and so forth. We've been working recently in testing out the VXLAN support, and that appears to be more or less working, but we want to, make sure it all works smoothly and is configured and running properly. And L3, there's, the Flavio and others have done a lot of work with distributed routing, and there's some other L3 work going on, so we'd like to see OVS with DPDK working well within that model. And some other things, we want the OVS with DPDK to not have to do any special configuration or whatever. We want the configuration of that to be automated and so forth. And of course, we'd also like OVS with DPDK to work well with some of the other OpenDaylight projects, group-based policy and service function chaining. And with that, I'll ask Danny to come up, and he's going to give us a good overview of the work that's going on in SFC that utilizes OVS with DPDK. And actually, before you come up, any questions at this point? One or two questions before we move on? Because this has been kind of the overview, and then Danny's kind of going to do a deep dive into SFC. Yes? How many CPUs do we have to reserve to run this? Maybe Danny has some. You have some information about that, so I think we'll get to it in Danny's. Excuse me? NUMA. That's part of the configuration. I don't know the answer. Go ahead, Uri. Okay. I think I'll pass it off to Danny now. Thanks.
Hello, everybody. My name is Danny Zhou from Intel China. I have a team in China to create open source-based server function chain vertical solution. Majority of my team member currently working on the SFC at the OpenDaylight project, and the rest of the team member currently working to contribute to vSwitch as well as SFC at the OpenFV project in order to enable a vertical server function chain solution. Okay. So what is server function chain? So basically, server function chain is about stitching different layer 4 to layer 7 network service in a particular order in order to provide network service to end user traffic. So in IETF, server function chain working group, they have a clear definition what component should be included in a server function chain. So basically, there are 3 different major components in server function chain setup. The first important one is service classifier. This guy receives traffic from physical NIC and do basic layer 2 to layer 4 classification, or do layer 4 to layer 7 classification if you have a DPI kind of functionality inside your classify. Without that, you just do layer 2, layer 4 classification. Then based on policy, downloaded from the SD controller, it could encapsulate the original packet with a new header, data plane header, which is called the NSH, standing for Network Service Header. As shown here, this is the packet packet format for the NSH header. Basically, it contains two parts. The first part is about the path information that can carry some of two fields, actually. Service path ID, which is a unique ID of the rendered system path. With this information, you can leverage the other two components defined in the spec. For example, service function forwarder, it can use this service path information and service index information in order to steer traffic with NSH header to a specific service functions. And also, the second part in this NSH spec is about metadata. So metadata here can be a fixed size metadata or variable size metadata. So with the service path information and the metadata, you can do service function chain. There are two different service functions currently are defined in the spec. One is the service function chain aware service function, meaning this service function is aware of the NSH. This is the new data plane protocol. Another is the server function unaware server function, which lacks either physical or virtual server functions. So for the SFC unaware server function, you need to have a server function chain proxy sits between the server function chain forwarder and the server function chain unaware server functions. Basically, the server function proxy manipulates the NSH header on behalf of the SFC unaware server functions. Okay. So how does a server function solution looks like in an NFS system? So this block diagram basically illustrates what a server function use case can looks like in an NFS system. On the top, it's a orchestration plus SDN controller. Currently, there is no open source mature enough VNF orchestrator in the market now. So OpenManual maybe is one. And in OpenStack, there is no one available there. There is a project called Tacker in OpenStack, but it's not an official OpenStack project. So what's the functionality that the OpenF orchestrator does is basically has two things to do. First is to define a VNF, not define just a image name. It also need to specify the functionality of this VNF, the vendor information, the CPU type, hypervisor type, as well as how many resources are required. For example, how many CPU, how many memory, how many storage do this VNF need in order to achieve the required bandwidth. So VNF orchestrator has another functionality is to deploy the VNFs in your service network. Okay. Once VNF deploys the function, the OpenDaylight, specifically SFC and OpenDaylight project, can do two other jobs, chaining and steering. In terms of chaining, it means it can use either SFC UI GUI or REST API in OpenDaylight to create a server function model. Once you create a model, you can use the data plane locator to map server function chain, a server function forwarder to the OBS, and maps the server function to VNF, which has been instantiated in your service network. And also, OpenDaylight, SFC and OpenDaylight project can, based on that service function model, to dynamically generate the open flow rules in order to program those open vSwitch running on different service node. So on the bottom, there are a bunch of standard high volume servers. Those servers are interconnected with physical network. For example, physical switch or physical router. And on each server, it actually runs a virtual switch. So as long as the virtual switch here is NSH aware, it should be able to to create the VTAP, which can use to encapsulate the original packet with NSH header, with VXLAN GPE header, for example. Also, the virtual switch here, we have different variants. You can use the stock OVS, which is kernel-based data plane. You can use the DPDK accelerator OVS. I'm going to talk about some performance data we have measured. It's experiment data, but it will show that DPDK accelerator virtual switch has much better performance than stock OVS. So virtual switch here basically can act as a NSH classifier. Okay, as I show here. Okay, this guy. The virtual on the service node A. So it does not actually run any open virtual machine on this virtual switch. It just do a basic 5-to-5 forwarding, but it's classify incoming traffic and add NSH header, add the VXLAN GPE header before the original packet, then forward to the next service node. On this service node, it also runs a virtual switch and also run a bunch of VNFs. So the vSwitch on those servers, like server node B and server node C, which actually act as a server function chain forwarder, which pass the packet with NSH header and steering traffic to a individual VNFs. Once the traffic with NSH header finish traversing the server function chain, your traffic will be sent to the classifier. It also virtual switch. We do decapsulation, meaning it removes the VXLAN GPE and NSH header and restore the packet to the original format and send it to the destination. Okay, so in FA system, there are lots of debate in the community about if I'm a telco or data center carrier, how I can ensure a physical appliance-based server function chain. It has much better performance than virtualized environment. If I want to migrate to NFV-based solution, how can I ensure it from performance process it can compete with the physical appliance-based solution? So using stock OVS, even if it has supported NSH, we according to our performance measurements, we found that without a DPDK acceleration, it will be very hard to achieve end-to-end performance. I mean, for example, meet 10 gig or 40 gig LAN rate. So that's the reason why we want a DPDK and the DPDK related hardware software optimization technology on Intel x86 server to improve the performance of the server function chain. So how NSH currently supported in SFC at the OpenDaylight and OVS project. So basically in OpenDaylight, it's the OSDB source-bound plugin already support to create a VTAP, which is VXLAN GPE NSH-based VTAP. And in OpenFlow project, it already, the OpenFlow source plugin, it already supports the NSH header. Specifically, it implements the NXM, meaning the zero extent match to OpenFlow protocol, in order to download the NSP, NSI related match field in OpenFlow via protocol to the virtual switch. So in SFC at OpenFlow project, it can dynamically generate an OpenFlow-based rule and leverage the OpenFlow source-bound plugin to download those rules to the OpenVSwitch in order to steer traffic along the server function chain. In terms of OpenVSwitch, so there are different OVS variants currently. First one is the stock OVS, and Cisco already developed a forked NSH patch, which is not upstream yet at the moment, but they have a forked OVS repository in the link over there. And it supports other NSH the OVSDB and OpenFlow in order to enable NSH-based server function chain. So, but that one is implemented in stock OVS, So the data plane sits in the kernel space. The performance-wise, it's not that good. But for DPDK accelerated OpenOS, actually the floating plane, data plane, sits in user space with Palo mode driver to significantly improve the performance of this virtual switch, roughly about 10x for small packet, 64-byte small packet. So both, and by the way, Intel also implemented an SSH-based patch. So it is currently not upstream yet, but we are working with Cisco together to upstream our NSH-based patch to the openvSwitch.org. So from control plane's perspective, the stock OS and the OS with DPDK are 100% same. But the data plane is not the same. So performance-wise, the DPDK OS is much better than the stock OS. So, but from feature-wise, the stock OS have a bunch of features that DPDK OS does not support. But from server function chain perspective, other features like full match action set, like Wixline GPNSH, those are basic functionality that are required by server function chain classifier and server function chain forwarder are already supported in the DPDK OS. So we actually do some performance measurement to enable OS as a server function classifier. On the top is a setup. Basically, we have two servers running server function, and those two servers are interconnected via a 10 gig or 40 gig switch. And we have a packet generator which generates thousands of row flows. So when the packet generator sends the row flows to the OpenVSwitch running on server 1, it just do some classification job first. Then it will encapsulate the original packet with the Wixline GP and NSH header. Once the encapsulation done, the traffic will be sent to the server 2, which runs the OpenVSwitch as well. On the OpenVSwitch there, do a basic decapsulation work, and then send the traffic back to the packet generator. We measure the performance of the stock OS and the DPDK OS. As the chart show here, using stock OS, you can roughly achieve 0.5 million packet per second for 64-byte small packet. But with DPDK acceleration, you can achieve maybe 2.2 million packet per second. It's about 5x better than stock OS. And also, if you just store less than 1K flows to the OS, you can achieve 10 million. So there are a bunch of performance bottleneck in current OS with DPDK NetDev. It's not for, the bottleneck is not from DPDK, actually from the OS user space data plane. So for example, it supports so-called 3-level flow cache mechanism. It supports a 1K exact match cache. This is a fixed size 1K. So if your flow, the number of flows exceeds 1K, you miss that flow table, then the OS need to make an up-core to the data plane classifier on a per packet basis. For that case, the performance is much worse. So, go ahead. Question?
So the exact match is mainly optimized by the fact that they need to calculate the hash. And you have matching on the hash in sequence of packets. But the hash is based on 5 tuple, which is also based, but in the middle you have the NSH header. So did you do something with the NIC to support NSH header in the hashing?
I'm going to talk about that, but currently it's pure software based. We use DPDK hash to match the 5 tuple. But actually, we are enabling some hard offloading based mechanism, which can offload sort of match from software to our firmware running on the NIC. And also, we have some sort of smart NIC solution, which has a switch silicon embedded in your NIC. That guy can do a match as well using TCAM. So, but for this performance measurement, we just use pure software.
So the hash calculation is on the part on
Yes. Yeah.
So why do you need a hash? The SFF should be a direct table lookup, right?
Sorry?
Using the path ID, you should be just a direct lookup.
Currently, because it's classified, so there is no path ID, right? It just because it receives row traffic, it only have 5 tuple with kind of information.
This is SFC.
Yeah, this is FC, but this is classified. Classified is not a certifying forwarder. So classified basically add a NSH header before your original packet. So the basic job the classified does is to match the 5 tuple for the original packet for the row traffic. Once classified done, it will add an NSH. So if you forward this packet to the next hop, to a certifying forwarder, that certifying forwarder actually they pass the information from NC header. But for this case, there's no.
Classifier performance, not
Yeah, as here. Yeah, I'm going to show another slide about the SFF performance. Okay.
Did you test this also in an NFV use case, like with no optimization for hash at all? Like you have millions of flows in every second?
Yes. That's this job done by DPDK, not by DPDK Access OVS. Basically, currently DPDK supports RT hash with a very high performance hash algorithm in DPDK. But in OVS, it uses its own hash mechanism. So, and in our current implementation of the DPDK Access OVS, it has not used DPDK hash algorithm not yet. But we are working with Nasir to replace that hash with the RT hash. In addition, in DPDK 2.2, we have a cuckoo hash-based, new hash algorithm. It can boost the performance for big table lookup than previous RT hash. So once that part is ready, and once the OVS takes that, the performance for big table lookup will be much better than today. Okay. So as I mentioned, there are a bunch of performance optimization we can do in the future by working with the openvSwitch.org to boost the performance with in the DPDK Access OVS. As I mentioned, hash is the first one, and the bunch of other one I'm going to talk about in the next slide. So another performance chart here is about the linear performance scaling with the multi-core. So on the chart in the left, it's actually the performance with a single core. But the question is that if you have a multi-cores to support the classification, can you achieve linear performance scaling? So according to our measurement, it is almost linear performance scaling with multi-cores. For example, if you want to support 40 gig line rate for small packet, you have to adopt multi-cores. And the steering traffic, not steering, is distribute different flows to different cores. Then those different cores can do, classification, encapsulation, okay. So this slide is about OVS performance as a certifying forwarder. So this can actually answer the question this gentleman has submitted about what the performance of the OVS can achieve when it acts as a certifying forwarder. So basically, we have a setup here. Still use the packet generator, but now the packet generator generates the VXLAN GP NSH flows, not just the row flows. So in this flows, it actually has a VXLAN GP header as well as an NSH header. So when this traffic is sent to a host, this host also runs OpenVSwitch, also runs the DPDK-based performance driver. So there are a bunch of rules, OpenFlow rules, have been programmed in the OpenVSwitch. They basically pass the VXLAN GP and NSH header, and based on the service path information and the service index information to steer this traffic from OpenVSwitch to a VNF. So VNF here is just a very simple L2 forward application, which is NSH aware, by the way. So once this guy receives the traffic, it just do a very simple task. It decrypts the service index, then forward the traffic back to the OpenVSwitch. OpenVSwitch here acts as a service function forwarder. So once the OpenVSwitch receives the traffic, send it back via DPDK PMD to the packet generator. We measure those kind of performance. According to our preliminary performance data, for this kind of physical to VM to physical type of use case, we can achieve 70% line rate of 40 gig traffic for big packet, specifically 1K big packet with 5 cores. But as I mentioned, there are lots of optimization ongoing. We are trying to optimize DPDK OVS with better hashing mechanism, with better use space warehouse optimization. For example, we're enabling zero copy, mod queue, those kind of optimization in DPDK as well in DPDK OVS in order to boost performance. So our target is to hit 40 gig line rate for 256 bytes with 2 hash word cores. It takes time, maybe. I'm not sure when we can achieve that, but there are lots of optimization ongoing. So we have a live demo here in Ballroom D. So it will be there till end of tomorrow. So basically, it's a vertical solution with a DPDK accelerated server function chain. It integrates the OpenStack to do basic network placement functionality. And it integrates the DPDK accelerated OVS in order to prove that using DPDK, you can improve the end-to-end server function solution performance significantly. And we also have some hardware offloading capability in our 40 gig and 100 NICs. So for 40 gig NIC, it is NSH aware. So basically, it can pass the NSH header and steer traffic from the NIC to the virtual machine where SRV VF interface. It's totally bypass the OpenVSwitch. And also for our 100 NIC, we are enabling some sort of hardware offloading mechanism. Currently, we are trying to offload VXLAN GPE NSH encapsulation, decapsulation from software to hardware. Okay. This is the last slide about our plan to support the server function chain. So the first thing is about the OpenVSwitch. As I mentioned, OpenVSwitch here can act as an SFC classifier and SFC forwarder. So we are keep optimizing the OVS performance in order to ensure end-to-end server function performance. And also, we are working with Cisco and Nicira, trying to upstream the NSH patch to OpenSwitch.org with DPDK NetDev support. In addition, as I mentioned, we are trying to offload VXLAN GPU NSH encapsulation, decapsulation from software running on x86 server to our smart NIC. Okay. In terms of OpenDaylight, we are working with community to add some new features like network placement, meaning we want to place the VNFs by leveraging existing infrastructure in OpenStack, such as the Glance, such as the Nova, such as Neutron, to start the virtual VNFs using existing capability in the OpenStack. And also, we are working on some advanced server function and server function path selection algorithm. Currently, the selection algorithm is based on round robin or random selection. We are adding some advanced selection algorithm like shortest path, weighted shortest path, load balancing to the SFC at the OpenDaylight project. In addition, we're also working on the GPP and SFC phase 2 integration. We want to add some advanced feature like end-to-end QoS, basically to rate limiting for the function solution. And thirdly, we also contributing to SFC at the OpenFV project because the SFC at OpenFV is a real vertical solution. When we talk about the SFC at the OpenDaylight, it's only an ingredient because it only sits in the SDN controller layer. There is no OpenF orchestrator. There is no OpenVSwitch integrated. So we are currently contributing to that as well. So, any question?
We support
Jennifer?
Do all the VNFs need to understand the header or like in your OVN?
I think the question is on the proxy.
Yes. That's it kind of need to be done by proxy. So basically, if you have a NSG unaware server function, if you steer the traffic with an header to this guy, it will drop, right? Packet will be dropped. So what server function proxy does is, it removes VXLAN GP and SSH header, okay, and save this header in a big table, and tag your original packet with a label. For example, it can be a VLAN label, or double VLAN label, or VXLAN, VNI label in a VXLAN header. So once you remove the header, you steer original packet with the tag to the NSG onward server function. This guy do packet processing as usual. Once the job is done, it sends the traffic back to the server function chain proxy. Its proxy look up the huge table by the tag, and find out the original VXLAN GP header, add it back to the packet. So this kind of thing can work. It works perfectly for stateless server function. But if you have a stateful server function like a TCP proxy or load balance proxy, it's still a question mark we need to resolve. Because for that case, you have to associate the new packet with the original packet. Because this kind of proxy terminates the connection with the client and establishes a new connection with the backend server. So original packet and the new packet are totally different kind of packet. The label information is missing. So you have to have a very complicated algorithm in your server function chain proxy to associate the new packet with the original packet. Otherwise, you cannot find the original VXLAN GP NSG header, which has been removed previously. Okay.
What's the first count you use in PNG to get these numbers?
Sorry?
What's the first count that you use in PNG to get these numbers?
32. Packet, yeah. You can easily change it to 64, yeah. But in our test, we use 32.
And the performance numbers were based on R2 blocks, right? It's just in one port and out another.
Yes, yeah.
Not bidirectional.
Yes, no separate, yeah. Okay, if no more question, that's all. Thank you very much. Yep.
Okay, let's get started. My name is Sharad Mishra. I work for Intel Corporation, and I've been contributing to OVSDB project for about 10 months now. And I have with me today Eric Multanen from Intel, and he's a contributor to OVSDB project. And I have Danny Zhou, also from Intel, and Danny focuses primarily on service function chaining project. And today we'll be talking about enabling data plane development kit accelerated open vSwitch in ODL and accelerating SFC. So just a show of hands. How many of you know what is DPDK? That's pretty good. So for the rest of you, what I'm going to do is I'm just going to give a brief overview of what is DPDK, just to level set. And then we will talk about DPDK accelerated open vSwitch. And then we'll go over and talk about what work went into the Lithium release of OpenDaylight for enabling DPDK in OVSDB southbound. And we'll talk about more work that needs to happen in ODL for DPDK enablement. We can work on it in Beryllium release. So we'll talk about those plans that we have. And then we'll move over to service function chaining, and we'll talk about
User space, and you can kind of, if you can see that in the diagram, it shows that the forwarding plane is up above the kernel space. And so that introduces a few issues that ultimately we need to work out and resolve. as we integrate with some of the other OpenDaylight projects. The other thing that gets introduced with OVS with DPDK is a number of different or new interface types. So the first one I'll call out is the DPDK. So I've listed the actual types. These are the strings that show up if you were to list the interface table in OVS-DB. You would see these as the type of that interface. So DPDK is the physical port. So because the data path is running in user space, the physical port is also managed by DPDK in user space and uses what we call a pull mode driver. And Danny will probably talk a little bit more about that in his presentation. But you see it there in the diagram called PMD. And so that type of port shows up as DPDK type. DPDK-R, the next type there is a DPDK ring device. That would be an interface that would be used for an application to connect to the forwarding plane, like a VM or something. And this is kind of special. It's basically a shared memory kind of interface. And so the application or the VM that uses this type of interface also has to have special interface or special device to interact with that type of interface. So I'm sure, like Sharad said, we just started coding in the last 10 months or so, basically the lithium cycle. So like Sharad indicated, DPDK is basically a library. It can be used for applications and a number of different things. What I'll talk about here now is, and again, this is a kind of an overview. It's not an in-depth study of vSwitch with DPDK, but basically using DPDK to accelerate the data path of vSwitch. And so I'll give you guys a brief overview of that, and then talk a little bit about how that gets enabled in Lithium in the OVS-DB southbound plugin, and then we'll move from there. So the diagram here is kind of showing at the bottom right there, it shows kind of a diagram view of vSwitch with DPDK, DPDK data path. One of the key things to, and then it shows it kind of in context with OpenDaylight and also OpenStack on top. From a control perspective, from OpenDaylight talking or communicating with the OVS with DPDK, there's not really any difference. It's OpenFlow and OVS-DB. And generally, it's the same. And the point today is to talk about some of the differences that pop up. So first one is OVS with DPDK NetDev uses the NetDev data path, which means that the data path runs in user space. It's not the kernel-based data path.
So apart from bypassing the slow networking stack, what DPDK also does is it uses pull mode driver, it uses batch packet processing, and it uses run to completion scheduling. So all those things combined together give DPDK a big performance boost. As you can see on the slide, this is running on an Intel Open Networking Platform system, L3 forwarding, using DPDK, and then without DPDK. And what you see here is the most gain in the performance you get on the smaller size packets. So for a 64-byte size packet, you go from 1 million frames per second to almost line rate. So that kind of improvements is what you see with DPDK. And that is the motivation for doing this enablement in ODL. And what we want is the consumers of ODL like OpenStack to use this information about the platform that they are managing, and then using that information smartly provision the VMs. Now I'll invite Eric to come on the stage and talk about DPDK OVS.
All right, thanks, Sharad. My name is Eric Multanen, and I've been working with OpenDaylight and the OVS-DB project for, well, at least a couple of years, actually. But
the performance improvement that we are seeing with DPDK in service function forwarder and service function classifier. And we'll also discuss the plans that we have around DPDK in SFC project. So this is not a DPDK presentation. As I said, I'll give a brief overview of DPDK and then level set everybody here about what DPDK is. I only have 2 slides on DPDK. And what I want to drive home with these 2 slides is the motivation behind enabling DPDK in ODL. So why DPDK and what does DPDK bring to the table? So what is Data Plane Development Kit? DPDK is open source software that improves packet processing on Intel architecture. And how it gets this improvement is that it bypasses the Linux networking stack and maps the hardware registers onto the user space. And then it provides a bunch of libraries like buffer management, queue management, memory management. And it also gives you some sample applications when you download from dpdk.org. And those sample applications are like L2 forwarding, L3 forwarding. And if you are a developer interested in writing your own DPDK-enabled application, you can look at those sample applications to get an idea of how to write your own DPDK application.